All right, in this screencast, we're going to look at acids and bases and the application of what is acid and what is base and some of the activities that you're going to be doing in this chapter. All right, so conjugate acid and conjugate base, and we talked about these briefly in the previous screencast on types of acids and bases. Think of the word conjugate as an opposite. So what I want you to keep in mind is that whatever acid you have, it is going to become your conjugate base, and whatever base you have, it is going to become your conjugate acid. Okay, so there's the pairs. What you're going to be doing is you'll identify the acid, so the substance that either has a hydrogen extra to be taken off, and when you take off that hydrogen, you then become the conjugate base. So we started with an acid of HCl, and then you strip it of its hydrogen. That's why it's an acid. It has the hydrogen to give up. So you take the hydrogen off of the HCl, and the remaining Cl minus is now the conjugate base. It can act as a base and take on a hydrogen, returning it to an acid form. Likewise, once you identify which one the acid is, the other substances are base. So in this case, water is a base. So water can take on the hydrogen, becoming an acidic substance or a conjugate acid of H3O+. H3O+ is also known as the hydronium ion. You will hear it referenced in problems as either just the hydrogen ion or the hydronium ion, and they are interchangeable. You need to recognize that they're going to be synonyms. So the terminology here is conjugate acid goes with the base, and the conjugate base goes with the acid. So this image right here is handy to have as an example in your notes so that you can see the relationship between the acid and its conjugate. So as we just saw in that previous example, water can act as an acid or a base. And when something can act as either an acid or a base, it's called amphoteric. It can either accept a hydrogen ion or it can give up a hydrogen ion. And so depending on what it's paired with is what it behaves like. Another tool that you need to be aware of is an acid-base indicator. When we were looking at the types of, between acid and base, some of the characteristics where they change in the presence of an indicator. So an indicator is a tool where you will put it into the solution, and it doesn't react. It's almost like a catalyst, but it doesn't react other than to change color in the presence of acidic solutions or basic solutions. So depending on what color your indicator changes to, you can determine if your solution is acidic or basic. We will use indicators. An example is phenolphthalein. We will use indicators in titrations. So if you start with a basic substance, whenever it changes back to not basic, the color change occurs and you can see it go from pink to clear. Water is really an incredible substance, but in this case of acids and bases, water can act as either acids or bases. So we've said that it is amphoteric, and it is also neutral. So it has a pH of 7. Here's the thing: water can self-ionize. So when you have water reacting with water, one is going to become an acid and one is a base. One of them is going to give up its hydrogen to remain an OH, the leftover part, and the other one is going to take on a hydrogen, becoming the hydronium ion. So water is, and this is at equilibrium, water is the basis of a lot of what we're going to be doing. So this K value here for this reaction that I just wrote up is going to be called KW because it's based on water. So at a very small amount of this reaction occurs, the K value is exceedingly small. You can see it here. It's 1 times 10 to the negative 7th. So we know based on equilibrium values, when the constant is small, it favors the reactants. So this one only ionizes a little bit. But this value here, this K, and this 1 times 10 to the negative 7th is a value that you can memorize. What happens then is that this value is both the H plus ion concentration or it's the OH ion concentration when it's water. So we can take and plug in 1 times 10 to the negative 7th into both the H plus and the OH minus, and you get this expression that KW is 1 times 10 to the negative 14th. This will be helpful when we're dealing with if I give you a hydrogen ion and I ask you to find the hydroxide ion. So you can always memorize that the water, the Kw, is 1 times 10 to the negative 14th, and this allows you to solve problems. Remember, Kw is a constant. It is not going to change, and for Kw it is 1 times 10 to the negative 14th. We are going to be able to find our concentrations of H pluses and OH minuses at different temperatures and different situations. But the 1 times 10 to the negative 14th is the value for Kw. Okay, and now we finally get to the heart of the matter here, pH scale. pH expresses a concentration of H plus ions. You can likewise have pOH, which expresses the concentration of hydroxide ion. Okay, the whole scale ranges from 0 to 14, and a pH of 7 is neutral. A pOH also of 7 is neutral. Okay, now this is where it gets dicey. If you're working with pHs, having a low number means that it's a strong acid, and having a high number means that it's a strong base. So we can take our pH and solve to find the H plus ion. pH is equal to negative log of H plus concentration. Okay. pOH is equal to negative log the OH concentration. We can further say that pH is plus pOH is equal to 14. So given these three different equations here, we can find a whole bunch of information. I can give you a pH and ask you to tell me how much OH is in a reaction. I can give you OH and ask you to tell me about the pH. As long as we are dealing with our pH scale, it works. Now, if you're asked to find the inverse, if they give you H plus and you want to find the pH, you use the inverse. So on your calculator, you're going to probably do second log, and that looks like 10 to the x, and that's what we're going to be spending some time. So you may need to do, remember that you have a negative exponent there. I promised to show you a brief screencast on how to use your calculator for this, and we'll talk about this in class. So make sure that you have your calculators when we get to this part. Here's a graphic showing you some real-life examples of things and how they have pHs. On the far side over here we have hydrochloric acid, and over here this is NaOH, so sodium hydroxide. You can see things like tomatoes and ammonia, and here's water, and what basic pH they have. Alright, when you mix an acid plus a base, it's called a neutralization. Okay, when you neutralize something, you make water and salt. And we're not talking table salt. It can be, but it doesn't have to be. A salt is a generic term for a metal and a nonmetal, or you can use polyatomics. But when this metal and this nonmetal, so this positive metal and this negative nonmetal mix together, that is a salt. So neutralization occurs when you mix an acid and a base together, and you are actually minimizing the effect of the pH and the pOH, and then you end up with a pH in the range of neutral, so like 7. And you can see that we have some examples here of neutralization. You have HCl and NaOH making NaCl and water. You have H2SO4 and KOH makes K2SO4 and water. So the NaCl and the K2SO4 are both salts. They are a generic salt.